Okay, so again, Laplace transform of function f of t, just defined as this relatively simple integral. Just to give you a picture of the integral, what we're doing is we're integrating this function, which is a decreasing exponential, with the function f of t. So whatever f of t is, let's just say f of t is a relatively simple function that maybe does something like this. So here's your e to the negative ts. Here's your f of t. If you multiply this function by this function, when t equals 0, this is 0. This is 1, the exponent 0. So e to the negative ts is 1. So that what you have is the product of these two is just equal to f of ts. By the time you get out to say here, e to the negative ts is about a half. So let's say e to the negative ts becomes a half right here. This means that e to the negative ts times f of t is now half of f of t. And then you get, let's say, half of that. That occurs maybe here. And you get maybe half of that. So you're actually integrating something that maybe looks like this and continues to go on to 0. As long as f of t is bounded, and as long as f of t doesn't grow faster than e to the negative ts decreases. There is that condition on the definition of the Laplace transform. F of t can't grow too fast because you want to have a finite integral. And you're not going to get a finite integral if f of t grows faster than exponentially. Okay, a little background to the integral, and okay, I'm trying to pin the video so I can see it. Okay, so there we have it. Now, this integral is pretty easy to calculate if it's pretty easy to calculate. In other words, if your function is reasonably well behaved. So, let's just calculate a couple. How about L of 1? Very simple function. F of t is 1, so you're just integrating e to the negative ts from 0 to infinity. Well, antiderivative of e to the negative ts with respect to t is just 1 over s e to the negative ts evaluated from 0 to infinity. At infinity, since this constant function doesn't grow too fast, you're just going to get 0. You know, just e to the negative ts is going to approach 0 as x approaches infinity. Incidentally, I have a negative out here. Okay? At 0, so it's 0 minus negative 1 over s times 1. And that's detail should be pretty obvious, so I'm not going to belabor it. So you get 1 over s. Very simple. Now, another important property, if f of t is a split definition function, defined to be 1 from t to, what's a good number to use here? From t to c. And 0 from 0 to infinity. Well then, L of f of t equals the integral from 0 to c of e to the negative ts times 1, and then the integral from c to infinity of e to the negative ts multiplied by 0. Well, that's going to give you, ultimately, this is just going to be 0. It's not going to contribute anything. This is going to give you negative 1 over s e to the negative ts evaluated now not from 0 to infinity, but from 0 to c. And this is going to be one over s, and reflexively I want to write 1 over c, and that's not even close. So using a little bit of mental activity, I'm going to get negative c over s, which of course equals one minus c over s. Okay. Now I've probably got room to do another one down here, and since I can't see the mouse, put the mouse up here, I can see it. Just looking to see how much board I've got to use down here. Looks like I don't want to get any lower than that. Okay. Now let's do Laplace transform of t. Getting hard to write down here. Bad looking infinity, and that's an even worse looking 0. But okay, we're going to get t e to the negative ts dt. And to integrate this, you've got to use partial fractions. So what we're going to do is we're going to let make sure I'm getting this, yep. Let u equal t, so the du equals dt, and let v equal dv e to the negative ts dt. I hope you can read this, but it's very straightforward, and if integration by parts isn't completely clear to you, review it. Okay, but I don't think it's going to be a problem for you. So then v could equal negative 1 over s e to the negative ts. So now this becomes the integral from 0 to infinity of uv, which is negative 1 over s, and I'll put the negative 1 over s out here. Times e to the negative ts dt, and I apologize, I got a little bunched up there. minus the integral of v du. So I'm going to do the minus, well, you're going to have minus the integral 1 over s e to the negative ts. I don't have a lot of room, and you ought to understand this. So I'm going to bring that negative 1 over s out with the negative here. It's going to give me plus 1 over s. Did I get that right? I think I did something in my head there. It isn't right. Because my UV will still have a T in it here. And over here, and so I'm going to have to rewrite that. I don't have room to squeeze in a T. I didn't write that very well in the first place. And I'm going to need to get things a little damper here. So maybe I ought to review integration by parts, but maybe I ought to just write it out carefully and completely, but I didn't leave myself room. So take it for what it's worth. Okay, this equals, okay, it's going to be uv minus the integral of v du. Okay, so it's uv, and it's not an integral. It's negative 1 over s t e to the negative ts. Then it's going to be minus the integral of v du, and the minus on the 1 over s will give us a plus 1 over s, which I bring out of the integral in advance. And then it's going to be integral of e to the negative ts dt. This is evaluated between 0 and infinity, and this goes from 0 to infinity. And I'm going to write it down here. This is going to equal what? At 0, you get negative 1 over s times 0 e to the negative ts, which is going to be 0. As t approaches infinity, t e to the negative ts will still approach 0. It's going to give you 0, which doesn't seem right, but I guess it probably, yeah, it's going to be right. Okay, so when we do this integral, we get, so this is 0. This integral becomes negative e to the negative ts over s squared, because of course when you integrate this you get a negative 1 over s, evaluated from 0 to infinity. And let's make sure I've got that. No, I've got it there. Why did I think I didn't have it over here? Well, there's the top of the mouse. Okay, I've got more room than I think. Of course, we're in the watermark here on the Zoom video, so I'm going to have to raise that up a little bit so we can make sure we see this. Okay, anyhow, evaluating this e to the negative ts at 0 is going to give us 1. Evaluating infinity is going to give us 0. So this equals 1 over s squared. Okay, so Pretty straightforward. Sorry I messed it up, but there it is. Now let's do okay. Another thing is, if we had t squared here, we would have to do integration by parts, and we'd have to do it twice. Because the first part would reduce the thing that we take the integral of to a t e to the negative ts, and then we'd still have to do that integral, and we'd end up with an s cubed down here. Okay, and since we have to do it twice, we'd end up with a non-zero constant, or a constant other than 1. And I think we're going to end up with a negative, so I think we'd end up with a negative 2 over s cubed here. You can check it out, you can do it. I could look at a table, and your book gives you a table of these things. But you want to be able to do the integrals. Okay. Now we could do Laplace transform of the cosine of t. Again, it's going to just involve an integration by parts. Integral from 0 to infinity of, put the cosine of t out in front here, e to the negative ts dt. Huh. You'd think I would have run into that little flaw on the board. There's a kind of a line that goes down to about here. Maybe that's new. Okay, so anyhow, we have this, so we're going to let u equal cosine of t dv equal e to the negative ts, so that du equals negative sine of t dt, and v equals negative 1 over s, this should have a dt on it, times e to the negative ts. Now this part gets kind of redundant when you're doing a lot of integration by parts. It's always going to be this, but what you get here will differ. And in this case, we're going to get something that we can't necessarily integrate without another integration by parts, and then we have there's a word for it, and I can't find the word, a recurrence, but you'll see what it is. Okay. So this is going to be uv, so it's going to be negative 1 over s cosine of t e to the negative ts, and then it's going to be minus the integral of v du. The minus and the minus 1 over s will just give us a 1 over s integral of sine of t e to the negative ts dt. Now this is not apparently getting us any closer to the integral than what we already had, but now we can evaluate this. Of course we need to 0 to infinity here. Okay. When s is 0, e to the negative ts is 1, cosine of t is 1, so we get a negative 1 over s. And then when as t approaches infinity, the exponential approaches 0 rapidly. The cosine of t is bounded between 0 and 1, so that this integral, or this expression, approaches 0. Okay, then we have integral of this. Now we're going to have to do another integration by parts. We're going to now let u equals sine t, du equals cosine t dt, dv equals e to the negative ts dt, so that v equals negative 1 over s e to the negative ts. Again, like I say, we get kind of used to this. Okay, so then we're going to have negative 1 over s plus 1 over s multiplied by the uv, which is, just being careful here, negative 1 over s okay, that's our uv from 0 to infinity. And then we're going to have to do the other part down here because I went and wrote this all out. Then it's going to be plus the uv, well, it's minus the v du, but you have a minus the 1 over s, so you're going to get a 1 over s again. It's going to be the integral then from 0 to infinity of v du. It's going to give you cosine t, not sine t. Now multiplying all this out, we get a negative 1 over s. Now this evaluated between 0 and infinity. At 0 your sine is going to be 0. At infinity, the e to the negative ts is going to approach 0 much faster than the sine does, so we don't get anything from this term. Then we're going to get a 1 over s squared integral from 0 to infinity so now what are we going to do? To evaluate this, by darn, we'd have to do another integration by parts, which would just lead us back to what we had here. And then we'd do another one and we'd end up with something like this, but another power of s. Now that's going to get to be, you know, kind of never ending, okay? We're never going to get out of that loop. So we have an infinite loop. However, this has to equal this, and this is the same as this. So now that's going to equal, well, getting ahead of myself, tells us that the integral we're after equals negative 1 over s plus 1 over s squared times this integral. So that if I subtract this from this, I get one minus 1 over s squared times that integral. And that equals negative 1 over s. And I need to put parentheses around this. so that this integral equals negative 1 over s divided by 1 minus 1 over s squared. Now, not sure I got all my arithmetic right. So I'm just going to say this integral, which goes from 0 to infinity obviously, is going to equal this divided by this. So we get negative 1 over s divided by 1 minus 1 over s squared. I don't have time to work out the algebra, but 1 minus 1 over s squared is s squared minus 1, s squared minus 1 over s squared using the common denominator. And what we end up with is s over s squared minus 1. Okay. And I kind of think that's right. Now I can double check myself, and it's probably worth doing that. Let's make sure that I got that right. But I'm going to go ahead and pause the video.
Recording stopped.
Because I think I got that right. And I'm going to pause the good video here and leave everybody in suspense. Look it up. It's right there in the first section. It looks right. We want to double check.